let us look at variable covalency. Variable means different valencies, like you have heard about ferrous and ferric. Similarly, in chlorine also we see different types of valency. Chlorine can show us valencies of 1, 3, 5 and 7. So how are we going to see that? If I look at the electronic configuration of chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. Now this still here is a complete shell, so I am looking at only the outermost shell. So 3s has 2 electrons, 3p has 5 electrons, and I can say that at ground state, initially chlorine shows valency of 1 because there is one unpaired electron. So depending upon the unpaired electron, we will say what valency is the element showing. Now in the excited state, you also know that in the third shell, we can have S, we can have P, we can have D. First shell can only have S, second shell can have S and P orbitals, and third shell can have S, P and D. So in this first case, 3D was vacant. There is nothing in that. I've written here excited state. In the excited state, S has these two. I am shifting this one electron here. So what will I have? I'll have these two are as such. One electron from here has gone here, and this was already here. So I've shifted these. So now there are 3 unpaired electrons. So now I'll say valency becomes 3. In the second excited state, I'll shift this one electron more here. So these are paired, but this becomes unpaired, unpaired, unpaired here and here. So now there are 5 unpaired electrons. So I'll say valency has become 5. And now I'm shifting this electron also here. So all of them become unpaired electrons, and so now valency becomes 7. So chlorine can show variable valency of 1, 3, 5 and 7. That is, it is going to make compounds, different compounds with different valencies. Now look at fluorine. If the question asked is, why does fluorine not show variable valency? That's because fluorine's atomic number is 9 and this is its electronic configuration. There is one unpaired electron here, so valency is 1. I cannot shift it anywhere because in the second shell there is no d orbital. There are only s and p orbital. So you will say chlorine is showing variable valency because it contains an empty d orbital where I can shift electrons and change the balance. Now similarly, we can find different valencies in case of phosphorus and sulfur. So you try and find out what valencies can phosphorus and sulfur show. Look at the atomic number of phosphorus is 15, this is 16. Exactly in the same way, try out, because in this case also it will become 15 will become 2, 8 and 5. That means we are in the third shell. So contains d orbital here. This also contains d. You can keep shifting the electrons till all of them have become unpaired and check on how much of the valency, what valencies can phosphorus and sulfur show. Now look at variable electrovalency. Now electrovalent compounds contain metal and non-metal. So metals lose electrons to show their valencies. So when you have learned about ferrous and ferric, meaning they have lost electrons. So variable electrovalency means how a metal loses electrons and shows different valencies. Cuprous, cupric, you have heard before. So there are 2 reasons for this. One is called unstable nature of core. Now unstable of nature of core means, like look at iron. Iron's electronic configuration is this. Now when I have written this electronic configuration, if it loses 2 electrons, its valency becomes 2. So Fe2 plus iron's electronic configuration becomes this. Now the part which is left behind, this is the part left behind, is known as the core. So unstable nature of core means this core is unstable because it can further lose one electron. We have learned before that if it loses one electron and becomes half filled, it will become more stable. So it further loses one electron and becomes more stable by becoming Fe3+. So we will say Fe3+ ion is more stable than Fe2+ ion, which means if I am looking at FeCl3, ferric chloride, which is more stable than ferrous chloride. So ferrous chloride, if I keep it in the open in my lab, if I have kept the bottle open for too long, it immediately oxidizes and changes into ferric chloride. Look at the second reason. The second reason is called inert pair effect. Now inert pair effect means if I am looking at 10 atomic number 50, I get this as the electronic configuration. Now in this electronic configuration you can see this part in p block elements. This part is the outermost shell. These are the valence electrons. So you have seen that the valence electrons are lost always. Valence electrons are lost. So that means 2 and 2, 4 electrons should be lost immediately and 10 should have a valency of 4. But it does not show the valency of 4 immediately because a pair of electrons in this case is inert, is not taking part in bonding, is becoming inert. So initially only p electrons are lost. When only 2 electrons are lost, it becomes Sn2+ ion. Further on heating, further on giving more energy, even these electrons get lost and so it becomes Sn4+ ion. So tin can show 2 types of valencies called Sn2+ and 4 as valency by losing first 2 electrons, then another 2. It is losing in 2 steps, that is why it is called inert pair effect. That is, one pair of electron initially is inert, does not take part in bonding. So we say this is the reluctance of the pair of electrons to participate in bonding, which is called inert pair effect.